1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people.
Right. So welcome everyone to the first seminar in the virtual seminar series for undergraduate physics students. We see people from all over Canada. Welcome. Today, this seminar is being recorded. So just to let you know, I would like to request everyone to keep your microphones on mute. And if it looks like you're running low on bandwidth, then you might consider turning off your video also. So today's seminar is going to be by Dr. Jeff Rau, who was an assistant professor at the University of Windsor, working in the field of theoretical condensed matter physics. He earned a BSc in physics and mathematics at the University of Windsor and a PhD at the University of Toronto. This was followed by postdoctoral work at the University of Waterloo and the Max Planck Institute for the Physics of Complex Systems in Dresden. His research broadly falls under the heading of quantum magnetism, with a recent focus on highly frustrated systems with strong anisotropy. So welcome, Dr. Rau, and we look forward to hearing your talk.
All right. Thank you for that nice introduction. Let me take over here if I can. All right. You all should be seeing my screen now. I assume there's no protestations to that it's working. So as teacher said, I'll be talking about skating on spin ice, a tour of frustrated magnetism and fractionalization. I apologize for the pun, but I was told that it would help get people interested, and so I begrudgingly made it. So I'm going to start this with a bit of a question. I think that'll lead in nicely into sort of the main body I want to talk about, which is, hold on. Okay. There we go. How can I make a magnetic monopole? Right, if you've taken an electricity and magnetism course, you'll know that the answer is you can't. Right, if I have something like a bar magnet illustrated here and I try to cut it in half, I don't end up with an isolated north pole and an isolated south pole. What I end up with is two smaller bar magnets. If I cut those things in half, I end up with even more smaller bar magnets as far as one can possibly go. Right, this is one of sort of the most basic facts about magnetism. It's been known, I think, basically forever. I think the first written reference to it is something like in 1200 AD. Can be stated a little more precisely in Maxwell's equations over here, where this basically says that the divergence of the magnetic field has to be exactly zero, right? Or more visually, you can think of that as magnetic field lines must always form loops. They can't start and they can't end, right? So why am I asking you if you can make a thing that immediately I'm telling you can't make? Well, I want to sort of explore around this question a bit and try to feel out how close we can actually get to something like a magnetic monopole, right? So we just saw that cutting doesn't work, right? Well, one other strategy one might do here is instead of trying to cut this thing, you might try to stretch it out. So for example, if instead of considering a magnet, a bar magnet like over here, be a little more, I think, intuitive to think of this more like a solenoid, a current wrapped around in a cylindrical fashion. This generates basically the same magnetic field. You have magnetic field lines going through the solenoid out one end, back through the other end, looping around, not stopping or ending. Another way to try to make one of these monopoles rather than cut this thing in half is to try to stretch this thing out, right? If I have magnetic field lines emanating from one end of it, magnetic field lines going into the other end of it, then you might think, well, if I can pull these two ends apart, really far apart, then maybe these two ends will look something like a magnetic monopole, right? So this is sort of the idea of what's called a Dirac string, where you take something like a solenoid, you make it very thin, and you stretch it out over a long distance, right? This magnetic flux gets confined to this tube between the two endpoints, but then shoots out at the end in an almost monopolar fashion, right? So here is an illustration of that. I apologize for sort of this somewhat crude sketch, where at one end, the magnetic field lines are going in. This is in some sense the negative charge. And then on the other end, the magnetic field lines are coming out. This is in some sense the positive charge, right? So this is not a great construction, right? Because now you have this tube, right, sitting there between your charges. You don't have that with something like electric charges, right? There's no string, so no solenoid connecting them, right? So, well, you could say, oh, well, let's try to fix some of these problems. I could make this thing really, really, really thin, so maybe you don't notice the tube, right? And this will make it more and more like a monopole, but you still have to drag around that tail, right? Even if I make that other end of this thing really far away, I still have this end here with this tube coming off of it, right? And so if you wanted this thing to be like a free particle, like some kind of a charge, then this is not good, right? You're dragging around a solenoid. Things get even worse if you try to think about, well, what if I want more than one of these things, right? You don't just want one magnetic monopole. What if I want 2, 3, a gas of them, a liquid of them, right? Well, now I have this sort of tangled mess of solenoids that I have to drag around, and I have to make sure they don't run into each other or tie knots into each other or do anything like that, right? And beyond that, here we're sort of permanently gluing 2 charges together, right? This positive charge here is always connected to the same, where's the other end of this thing, negative charge over here, right? So there's this sort of unnatural pairing up of these things because of these solenoids that also is not ideal. Okay, so hopefully I've dissuaded you a little bit from that idea, but what I want to try to convince you in this talk is that exactly this kind of thing, free of most of these issues, can actually emerge in a solid state material through a process known as fractionalization, right? And hopefully the broader lesson here, I'll be able to show you that these kinds of solid state realizations of things, these kinds of exotic materials can lead to types of particles, types of order, types of physics that are hard to get anywhere else, right? That might seem, somewhat unnatural. This tangle of solenoids might seem like a really contrived construction, but we'll see in a certain class of magnetic materials, this actually shows up pretty directly, okay? So that's my sort of basic plan here. I'll first talk a little bit about magnetic materials and what are called Ising models or Izing models, just to lay the groundwork. Then I'll tell you about the process, the property of frustration that enables a lot of this to happen, and go through in detail how this all works for a sort of simpler 2-dimensional version of this physics, which is called square ice. Then I'll tell you about the more realistic 3-dimensional spin ice, a little bit of broad discussion about what this means more generally, spin liquids and fractionalization. And then at the end, hopefully in the last 15 minutes or so, I'll tell you about some work that's of mine, more directly about some work of mine that'll justify that pun, which is about spin ice thin films. Okay. So let me remind you a little bit about some of the foundations of magnetism here, right? So what we're thinking about is material. So this will be something like atoms forming some kind of crystal, which I've drawn a cartoon of on the left here, some sort of crystal of atoms forming some grid. On each point of the grid, I have, maybe that's an electron density, I have an atom, right? Typically atoms, in many cases, can carry magnetic dipole moments. This could be, for example, from the spin of the electrons. This can also be from the orbital motion of the electrons, right? Generally, this kind of atomic physics can get quite complicated. These things can point in different directions. They can have different anisotropies. They can be a bit of a mess. What I want to focus on is sort of the simplest version of this, where we say, okay, each atom in our crystal carries a magnetic dipole moment, but this magnetic dipole moment can only point in 2 different directions. Okay, so one of the directions here, I've illustrated it in 2 different ways. Both of them will be useful in what I'm going to tell you. So here the magnetic dipole moment is pointing along this arrow. I'll call this up. If you want to think of it like a current loop, it's going counterclockwise as indicated for that atom. And I'll label this as +1. So this sigma will tell me which direction this is pointing, and +1 tells me it's pointing up in the vertical direction. And then in this simplest case, I'm just saying I have two possible directions. So I can't put this in X, I can't put this in Y. I can only put it opposite to that red arrow, right? So this blue arrow is going down. This current, if hopefully I've drawn it correctly, is going clockwise now. And I'll label that blue arrow as sigma is -1. Okay, so there's a lot more you can get in magnetic materials. It's not always just two states. You can have 3, 5, 7, quite a lot of degeneracy in atomic systems. You know, there's a pretty big periodic table and there's a lot of varied behavior in it, but this is sort of the essence of what we're going to need here. So these kinds of spins where there's only two possibilities, here up or down, are what are called Izing spins or Izing spins, if you pronounce it more correctly, as they would in Germany, say, are going to be the focus of what I'm talking about. Okay, so we have some kind of crystal. On at each point of the crystal, we have an atom. Each one of these atoms carries a magnetic dipole moment, and these dipole moments can only point in one of two directions. Say up, we'll call them up, and we'll call them down. All right, so if that's all we had, it'd be a little bit boring, right? Just isolated up or down doesn't really do too much. We have to have these things talk to each other. They have to interact. Okay, so when spins interact, this is typically called exchange interactions. This is sort of a historical term because of one of the dominant interactions is in a certain class of systems. Here, we're not going to go into the details of where exactly this comes from, but let me just tell you that for Izing spins, there's generally sort of two tendencies you can have, which is if you have two of these spins, you could have a tendency of them to align, or you could have a tendency of them to anti-align with its nearby spins. So for example, if it tends to align, we call that ferromagnetic. So here, two of these atoms are placed near each other. They interact through these exchange interactions. If those are ferromagnetic, the lower energy state is the one where they're pointing in the same direction, and the one where they're pointing in opposite directions is a higher energy state. Conversely, if there's a tendency to anti-align, call that antiferromagnetic. Them pointing in the same direction is disfavored. Them pointing oppositely is favored. Okay. Now, we don't just have two of them, we have a whole lattice of them, but for some certain simple cases, this is not much of a big deal, right? If I have, say, one spin pointing up here, I've sort of drawn them on the diagonal just so we can see them a little better. So just keep in mind, there's still two here. I just angled them for visual purposes. If this one is up, then the best way to assign its neighbor, if they're ferromagnetic, if they want to align, the best way to minimize that energy is to have that one also be up, to have the neighbor of that be up, to have the neighbor of that be up, to have them all be up, right? That will give you the lowest energy, right? I didn't have to start with up here, though. I could have started with down, and you get the same picture, right? So with these kind of interactions, at least when these crystals are somewhat simple with ferromagnetic interactions, this minimal energy state is basically unique, right? We just have all up or all down. Okay, these are essentially two states that are related by symmetry, by reversing time, essentially. You reverse the directions of magnetic dipole moments. For the antiferromagnetic case, this can also be true, right? So here, for example, if these are arranged in this grid just like above, if I make this one red, they want to anti-align with its neighbors. That one wants to be blue. That one wants to be blue. Okay. This one, it wants its neighbors to be red. This one's red. Still good. We can continue along the lattice in that way and fill the whole thing out, right? In each one of these things, each one of these arrows connected by a line, by an exchange interaction to its neighbor, is completely satisfied. It has its minimum energy state. Blue and red, blue and red, blue and red. And just like the other case, there's another one by flipping them all, switching red and blue, but that's not essentially different. Okay. So for both cases, there are arrangements of these spins where these exchange interactions can be completely satisfied, where you can just sort of tile out these spins in some way over the whole lattice without much trouble. Just for a little bit of a technical note here, this is typically encapsulated in an energy that looks like this. So this is the energy of all these spins. This is a sum over all those neighboring pairs. So this I and this J would label the atoms, and this sum would go over all of these pairs connected by these black lines. Okay, all the neighboring spins. These sigmas represent those directions, plus or minus 1. And so we're just multiplying them together on that bond on these two neighboring spins. And so if we want them to have a tendency to align, all we have to do, okay, well, that should be less than 0 up there. I'm sorry. J should be negative here. It's always off to a good start. If J is negative, they have a tendency to align. If J is positive, the lowest energy state has them anti-align. Right here that have +1, -1, that minimizes the energy. So this is called an Izing model. So is this what always happens, right? So here, if I tell you that they have a tendency to align or a tendency to anti-align, I had no trouble filling these lattices out, figuring out what the best way to arrange them was. Is this always true? So the answer is no. We can't always satisfy all of those interactions pairwise. It's not always possible. When it's not possible, we call the system frustrated. So a simple example would be something like this, where I have 4 spins. So here I've changed it a little bit. So these black lines still mean these guys want to interact. I'll have them be anti-ferromagnetic. So they want to anti-align with along these black lines. But I'm also going to connect them across the diagonals. So each spin really wants to anti-align with all the other spins, all 3 other spins. Okay, so let's try to fill this out. Well, if I put up here, it wants to anti-align with, say, this one below it. So I can put down. So that's satisfied. That has the lowest energy. But, well, what do I put here? If I put up, this one's good. It's anti-aligned. But now this one's not. It's aligned. Right? If I put down, this diagonal one's good, but this one's not. Right? So because of the way these things are connected, by putting these diagonal exchange interactions, wanting the spins off across the diagonals to anti-align with each other, we can't satisfy every possible pairing of those spins. So there's no simple way to satisfy all those interactions. So the way to think about it, instead of having one best way to do it, what we have are 6 equally bad ways to do it. Okay. So, well, we can't make this as low as possible, as you might think, by making them all anti-align. The best we can do, it looks something like this, where 4 of the bonds are satisfied and 2 are not. So here we have 6 bonds, the 4 on the edge, the 2 crossing the middle. If I put the spins up, up, down, down, then these vertical bonds are satisfied, they're opposite. The diagonal bonds are satisfied, they're opposite. The horizontal bonds are not. Right? And you can play with the different permutations and combinations here, and you can see that no matter how you do it, the best you can do is have 4 of them satisfied and 2 of them not satisfied. And these are the 6 possible arrangements for that to happen. And so those 6 equally bad states, those lowest energy states, which can't satisfy all the bonds, each have a simple pattern, which is they're basically all the states where 2 of the spins are up and 2 of the spins are down. Okay, 2 up and 2 down. Okay, well, you might be thinking, well, maybe this will fix itself. This will resolve itself when I put more of them together, right? This is just 4 of them. 4 spins may not be enough. If I try to glue these together into a lattice, yeah, maybe that'll fix this, and I'll just pick out 1 or 2 states like we had before. So the answer there is no. But before I get into that, let me just do a slight change in perspective here. This is really just notational. So here I was drawing them as up and down because I want to talk about materials where these represent real physical dipoles. I'm just going to rotate these things a bit, sort of like 45 degrees. Okay, so instead of drawing 2 up and 2 down like this, I'm going to draw them like this, and I'm going to say 2 in and 2 out. So this down has become spins pointing in, and this up has become spins pointing out. Okay, it's just a relabeling. If you don't like that, you can just follow the colors, right? You can think here, red is different than blue. Those are anti-aligned. Red is the same as red. Those are aligned. Okay, but this will be much more natural when we do a little bit of the stuff I'm going to do in the next few slides if I just rotate these things 45 degrees. So this 2 up, 2 down rule then becomes, in this language, 2 in, 2 out. Okay, and you can always just follow those colors. Right. So let's move to the lattice with that new perspective. So the lattice, I'll glue them together in a way which makes what's called a checkerboard lattice, which is basically I'll just take these little squares with the diagonals and I'll glue them together at the corners. And importantly, I'm going to leave one of the squares here without diagonal interactions. So it's sort of, this is how it's arranged like a checkerboard. So this is a lattice called a checkerboard lattice. On this model, when you put the tendency to anti-align between these spins is called square ice, or in some senses, a 6-vertex model. So does moving to the lattice fix this, right? So we had 6 of these states that are equally bad. And now if we put more of them together, do we just pick out one of them? Answer right here, no, right? So suppose I started in the bottom left here. I picked one of these 6 states. If I go to the next square with the diagonals, I have more than one choice, right? This guy is red, this guy is in. I could put blue, blue, and red here, but I could have also have done red, blue, and blue. I could have also have done red, blue, and blue here across the diagonals. So even though I fixed this, I still have 3 possible choices that I could make here. And this set of choices doesn't diminish fast enough as you move through the lattice. So I have 6 choices for this first one. I have 3 choices for this next one, 3 choices for this next one. I keep going that way. I get a very, very large number of possible states that all have the lowest possible energy for this system. They're all equally bad in some sense. They're not completely satisfied, but they all have the minimal energy for this Ising model. And so you can actually make this quantitative, and this is something that was done by Lieb quite a long time ago. You can actually count how many different ways there are to do that. And the number comes out to be exponential in the number of spins. So the precise number is 4/3 to the power of 3n/4. So this is the degeneracy of the ground state, the number of states with this minimal energy. And another way to think of this is, if you don't want to think about just the degeneracy of the ground state, you can think of this as the entropy of the system is non-zero at 0 temperature. So this is called residual entropy. It's basically just the log of this. And you have an entropy because of this something to the power of n. You have an entropy that is actually proportional to the number of spins. So a finite entropy density at 0 temperature. So we found this model with a huge, huge number of minimal energy states, right? And these minimal energy states are made up of these squares where you have 2 of the spins pointing towards the center, 2 of the spins pointing away from the center. Okay? 2 in, 2 out. What does this have to do with magnetic monopoles? So what I want to try to illustrate for you here, and again, I apologize for my somewhat crude drawings, is that this 2 in, 2 out rule actually defines, in some sense, this divergence of B equals 0 constraint like you have in magnetostatics. And the way to think about this is to look at these arrows and try to follow them around the lattice. So suppose I started at this red arrow here in the upper left. If I follow the arrow across the tetrahedron, I get to this blue one. Here, I want to keep going head to tail. So let's go to this red one, to this blue one. If I follow them head to tail along the lattice, you can see that they form these lines. And if I kept going, if I drew a bigger picture, you would see that these things actually close up somewhere in the lattice. So because of this condition, that these things have the minimal energy to be in this very large set of ground states, it forces these spins to form these loops, where if I follow them head to tail, they eventually come back on themselves. So I've drawn several of them here. Every single spin in this thing is in one of these loops. So this blue loop is different than this purple loop, is different than this pink loop, but they all close, right? And so this is a kind of emergent version of this statement that magnetic field lines form loops, right? Now, this is really not a statement about magnetic fields. These arrows could represent anything right now. They could have been electric dipoles. They could have been something else, right? this is just a constraint from how those exchange interactions forced them to point relative to their neighbors. Okay, so we have an emergent version of this divergence of B equals 0 at this lattice level. Okay. In these systems we're talking about, these things really are magnetic dipoles, though. So we can actually talk about their magnetic fields. And if you think about how this would go, you know, a chain of arrows like this, head to tail, right? If I drew this a little more schematically, it might look something like this over here, a chain of dipoles head to tail. Now, if I thought of these instead of as being these arrows, if I thought them as current loops, right? I'd draw the current loops like this in the plane defined by that arrow. And as I, you know, go along this loop, you might think, well, if I have enough of these things, it kind of starts looking like a solenoid, right? I have a chain of dipoles. Each dipole is like a little current loop, right? If I have a big stack of current loops, that's a solenoid, right? They're all going in the same direction because they're going head to tail. So this thing is sort of has a magnetic field, which is essentially that of a solenoid, right? And if you remember what the magnetic field of a solenoid is, when it's closed like this, when it forms a loop, it's basically 0 outside, right? Here, this is not perfect because these loops aren't continuous in some sense. There's gaps between them. There'll be sort of fringing fields at the atomic scale, but for the most part, the magnetic fields from these loops of magnetic dipoles will cancel, okay? And so this is our first ingredient, right? Is we have this emergent version of div dot B equals 0, this emergent statement that these loops of these spins of these arrows have to close, right? And because it's emergent, it's not fundamental. It's not, you know, something from high energy physics in some sense. We might be able to break it. We should be able to break it, right? And because these arrows actually are magnetic dipoles, they carry a magnetic dipole moment. When we break this emergent constraint, what we're going to see is that the magnetic field from these dipoles is going to look a lot like what you get from breaking the underlying physical constraint. They're going to look like magnetic monopoles. So let me just tell you a few little facts about these loops before we get into that, which is they're everywhere. So I showed you that every one of these spins was in one of these loops. And beyond the fact they're everywhere, they're not actually uniquely tied together, right? So if I follow this pink loop here, right, when I got to this shaded square here, I had two choices which way I could go, right? If I'm going head to tail, means I'm going blue to red. I could go this way, or I could go this way. It's not uniquely defined. So when I draw these things, I don't have to draw them like this, where they cross, one goes under the other. I could have drawn them like this, equivalently, that they actually avoided crossing. Okay, so unlike our picture of this tangle of solenoids at the beginning of this talk, these loops are a bit more tenuous in that they're not, strictly speaking, glued together in some tight way, right? There's a little bit of ambiguity when they cross, and that ambiguity means you can sort of assign them, assign spins to loops with a little bit of freedom. And secondly, you can actually move them around. This is just labeling them differently, but you can actually move them around without any cost in energy. So for example, looking at this configuration again, if I draw this pink loop here, going through here, I draw this purple loop here. What I can do is if I take all the spins on this green, at the edge of this green square, this blue one, this red one, this blue one, this red one, if I reverse all of them, so blue went to red, red went to blue, all the way around, all four spins, then I've changed my configuration of these spins, but every one of these squares still has 2 in or 2 out. I didn't break any of these. I didn't make any of these things not have the minimal energy, but I did rearrange these loops, right? This loop here had to go either this way, up and to the right, or down and to the right before. Now, after I flip this thing, this loop has to go down and to the left or up and to the right. So the possibilities are actually different. So it's not just that they're not stitched together in some well-defined way, but they can actually be rearranged at no energy cost, right? So what you should think about this is we sort of have this soup of these loops, of these sort of approximately of these magnetic solenoids filling the whole lattice, okay? And these things can be mixed and flipped and rearranged in prescribed ways at no energy cost. Right, so how do we actually get these monopoles? And so to get a monopole, what we're going to do is we're actually going to cut a loop and essentially get a pair of monopoles, and then we're going to pull them apart. So let me just illustrate how this goes at the level of these spins, and then I'll decorate them with this picture of solenoids so we can see that these things are actually monopoles. So what I'll do is I'll make sort of the simplest excitation of the system. So an excitation here means it has an energy above this minimal energy, above the ground state energy. And to do that, the minimal excitation here would just be I take one of these spins and I flip it. Okay, so if I flip this blue spin here, I turn it red, then this square here, which has 2 in, 2 out, this square here, which has 2 in, 2 out, now doesn't. This one has 3 out, 1 in. This one has 3 in, 3 in. That is not written correctly again. 1 out, 3 in. Sorry about that. This one has 1 out, 3 in. Okay, so this costs some amount of energy. This will be naturally generated in a whole bunch of scenarios, right? If I'm at some finite temperature, these kind of excitations will get thermally populated, right? You'll have some Boltzmann weight that'll tell you that these things are there with some fraction. You can also intentionally excite them with things like light or neutrons or all sorts of experimental probes. Okay, so by flipping that one spin, we made an excitation. And I've indicated here by a red ball and a blue ball that these two tetrahedra are now not 2 in, 2 out. They're 3 in, 1 out, 3 out, 1 in, or 1 out, 3 in. Okay, so that's our excitation. So the thing I want you to see about this is because of the same fact that we can rearrange these loops, we can actually pull these defected tetrahedra, the defected squares, the 3 in, 1 out, the 3 out, 1 in, or the 1 out, 3 in, we can actually pull them apart at no energy cost. So one way you can see this is just start flipping spins, right? So if I start where with that configuration from the previous slide, and I flip this spin here, then what happens is that square that had the defect before, that had 3 out, 1 in, now does not. It has 2 in, 2 out. It's good again, right? But the other one that was connected to the place I flipped it is now has a defect. It's 3 out, 1 in. And I can continue this. I flip this one here, this guy moves over here. I flip this one here, this one moves over here, right? And so through this whole process, this energy cost hasn't changed. Still only 2 of these squares are not in the lowest energy state. Only 2 of them are actually excited, right? But what I can do, what you can see that I can do here is that I can actually, by rearranging these spins in between, by rearranging these 2 in, 2 out states, I can actually pull them apart. I can actually pull them arbitrarily far apart, all the way across the crystal, if I, was willing to draw a figure that big. So the way to think about this is these things cost energy to create, but they don't cost energy to separate, right? And so these things are actually free to move. Okay. They're created in pairs, but once they're created, they're free to move. And these are the magnetic monopoles. The way you can see this is just sort of by analogy here. If you look at what happens to these loops, right? Remember, we were interpreting these loops as solenoids in some sense, right? Once we've made these excitations, we now have loops that don't necessarily close, right? So here, for example, this thing here can stop at the other defect. We can start at one defect, stop at the other defect, right? And just like what we had when we didn't have the defects, we can think of this as a solenoid, but now if it stops, it means we have an end, right? And so you should compare this to this picture I drew for you at the beginning of a solenoid that I stretched out, right? This is kind of an atomic scale realization of this idea, right? And this is an explicit example of what's called fractionalization, right? Where we started with a system of magnetic dipoles, and this excitation, flipping that spin, changing the magnetic dipole, is now has the character of magnetic monopoles. What you would get if you, were able to cut this dipole in half. Okay, so from this we can conclude that the lowest energy excitation in this system are effectively magnetic monopoles. Okay. So I just want to stress here, because there is a group or a class of people who make a very big deal about these not being fundamental. They are not fundamental. So these aren't fundamental particles. We haven't, this kind of thing isn't discovering a new fundamental particle. It's an emergent phenomenon. So people do search for fundamental magnetic monopoles. These are not them. That's a very different question. That's about high energy physics. Here, what we're asking is, can we find them by essentially, instead of looking for them in the ground state of our universe, can we, in some sense, swap out our universe for the universe of this magnetic material, right? And here, what we're seeing is within this magnetic material, these things do pop out. So not fundamental. These are an emergent phenomenon. So there's a lot of physics here. A lot of it I won't have time to go into, but you can simulate these models really easily on a computer. So here I'm showing you a Monte Carlo simulation at finite temperature of this exact model I just showed you, an antiferromagnetic Izing model on a checkerboard lattice. This is at some finite temperature, so that there are some finite density of these excitations hopping around. And I've labeled for you on this thing using the lines, the different loops you have, and I've labeled for you using red and blue the defects. So you can see that in this simulation, there's a whole bunch of these red and blue, positive and negative monopoles, these defects jumping around from place to place, diffusing around. Let me see if I can restart that. They're at finite temperature, so they don't, propagate cleanly. They diffuse around. And if you watch them carefully, and if you went to lower temperature, you'd actually be able to see that there's a little bit of an attraction between the blue and the red. They tend to come together as they diffuse around. And so this is actually a result of what's called an entropic force. Basically, when you have these things, the number of states you have when you have the two monopoles versus when you don't is actually lower. And so because you want to maximize entropy, you want to bring these two things together and annihilate them. And this actually gives an attraction between them. And this attraction actually takes exactly the same form as the usual Coulomb attraction you would expect for electric or magnetic monopoles. If you want to play with that yourself, I've got this simulation's up on my website. You can play with it. It runs in the browser. It's just a little bit of JavaScript. But if you fiddle with the temperature, you'll be able to see how this happens, how they end up attracting to each other, how they pair create, how they rearrange these loops, how they diffuse around the lattice. Okay, so that's sort of the fundamentals. I want to tell you a little bit about that's sort of a toy model in some sense. I want to tell you about what these things look like out in the real world in materials. So most of what I said is going to transfer over very completely. The main difference here is that the geometry of these real crystals is just more complicated. So the real materials that realize this physics, so-called spin ice materials, are typically on what's called a pyrochlore lattice. So this is a three-dimensional lattice. It's a network of corner-sharing tetrahedra. So I've illustrated a small piece of it here. So each one of these little balls is a rare earth ion, which is magnetic, and typically it's a trivalent rare earth ion. And this kind of construction here is sort of like a three-dimensional version of that checkerboard lattice that I showed you before, right? If I sort of flatten this out, it would look a lot like these pictures I've been drawing for you, right? Each one of these four spins in each tetrahedron is connected to the other four spins, and they're glued together at the edges here, right? Here, it's just done three-dimensionally. Okay, what I'll tell you about are two of the sort of best examples, which are it's called Dysprosium Titanate and Holmium Titanate. They're just specific materials that have been best studied. There's maybe a half dozen more that have been discovered since then, but these are sort of the high watermark for actually seeing this physics. How does this work? Well, first thing we need, if we're going to realize what I just told you about, we actually need spins that are Ising-like, that they're actually two states. Thankfully, these rare earth ions give us that. So, for example, for this dysprosium 3+ ion, if you go through Hund's rules, what you find is you get a gigantic amount of angular momentum for an atom, total angular momentum of 15 halves, which is some combination, a pretty even combination of orbital angular momentum and some amount of spin angular momentum. So both spin and orbital angular momentum are significant here. And then because of that, these charged ions that actually surround this thing in the crystal. So for example, in Dysprosium Titanate, this dysprosium ion would sit here between these two tetrahedra. And then around it would actually be the oxygens that sort of fill out the charge balance of this structure. Okay. And these charged ions that make up the rest of the crystal exert electrical forces here, right? Now, if this was just spin only, that really wouldn't do much, right? It's magnetic dipole moment. Electrical forces don't do too much to it, but there's a huge orbital component, right? And so, you know, the electric fields or the changing electric fields in space because of this ring of oxygen ions, for example, end up splitting up this manifold you'd get from Hund's rule and picking out two states. Okay, so this is called a crystal electric field effect. And what it does, it essentially picks out two states which have the moment sort of maximally either along this axis or maximally against it. So this total angular momentum Z is in this direction, either being plus 15/2 or minus 15/2. Okay, so because of these crystalline electric field effects, you get Ising-like spins with only two states. And just like that, those pictures I drew for you, those two states either point into the tetrahedron or out of the tetrahedron because of this geometry. I do want to point out something here, which is because this angular momentum is so large, the magnetic dipole moment associated with each atom is actually quite huge, is gigantic as well. It's something like 10 Bohr magneton. Okay, that's big for an atom. Because of that giant dipole moment, the interactions between them are mostly just usual dipole-dipole interactions you would study in magnetostatics. Okay, you have two dipoles sitting some distance apart from each other. They have some orientation. You can compute what their interaction energy is, those dipole-dipole forces from usual E and M. Okay, since there's only two states, it's easy just to figure out what the tendency is here. I'm going to draw them just suggestively as little physical dipoles made up of some fictitious magnetic charge. I'm just doing this so that we can, we don't have to, do the dot products in the dipole interaction, right? If you take these two things, you point two of them out of the tetrahedron, you can think of it as a negative charge here, a negative charge here, a positive charge here, a positive charge here. Those two things repel. This kind of configuration will be disfavored. If you go the other way, one out, one in, the opposite happens, right? The negative charge here will attract the positive charge here. This configuration will be favored, right? So this is just like what we had before for those pictures I drew for you, where it's favoring them to be, in some sense, anti-aligned. Really, it's favoring them to be two in, two out, like we had in that two-dimensional model, in that toy model that we could draw pictures of at least a little more easily. So let me just give you a cautionary note here. The full picture here is significantly more complicated. It's not just dipole-dipole, though dipole-dipole is the biggest contribution. There's a contribution from super exchange, which is actually comparable to it. And you have to consider a really terrible slate of multipolar interactions if you want to get this right. But if you do that, you'll find that the final result is basically unaffected. So the answer still ends up being that we're favoring two in, two out, but just the root goes through a bit of a detour to get there if you consider all of the physics. Okay, so we have the same ingredients that we had in this two-dimensional case. And so we can draw precisely the same pictures as we did before, right? Each one of these tetrahedra, like each one of these squares, is going to have two of their spins pointing in and two of them pointing out, right? And just like those squares, there can be many, many different ways to glue those things together, right? So here's a cross-section of where I've sort of just filled them in somewhat randomly, two in, two out, on every single one of these tetrahedra. And so just like the two-dimensional case, there's an exponentially large number of ways to do this. Many, many minimal energy configurations, many, many ground states. Okay. And just like in the two-dimensional case, we could follow these arrows and form loops. We can do exactly the same thing in 3 dimensions. If I follow these arrows head to tail, they'll always end up closing up and forming loops, right? And exactly like the two-dimensional case, if I flip one of these spins, break one of the loops, I'll make a pair of magnetic monopoles. A pair of magnetic monopoles I can actually pull apart, right? And this was essentially a consequence of these first two statements, right? Once we had this very large ground state degeneracy, this very large number of minimal energy configurations, once we knew that they were formed these loops, then that implied that these excitations that break these loops actually had the character of magnetic monopoles. Okay. So geometrically a little more complicated, but the essence of it is the same. And so let me just do a little historical detour here, which is, well, I've been calling this, I've said the word spin ice a few dozen times at this point. Why is the word ice in there? What does ice have to do with any of this? Well, the problem of locating the protons in water ice is actually quite similar to the problem of orienting these spins, arranging these spins in spin ice. Basically, this is a picture of hexagonal water ice. This is a water molecule. And if you think about how hydrogen bonding works, this hydrogen is going to want to be sort of pointed at the neighboring oxygens, right? Two of them are going to be attached to that oxygen. It's a molecule, of course, right? But you have to pick which two neighbors these blue hydrogens actually point at to get that that energy gain from hydrogen bonding, right? And so two of them are going to be close to this guy, and then its neighbors are going to try to do the same thing. It's going to have hydrogens pointing at this oxygen too, and so two of them are going to be farther away. So two of them are close, two of them are far. So this maps directly to this 2 in, 2 out that we talked about for spins, right? You can basically map this close hydrogens to say arrows pointing out, and then these far hydrogens as arrows pointing in, right? And so you get almost the same physics. There's sort of complicated reasons why spin ice is a little bit nicer to study than water ice. The fact this is hexagonal and ice has, you know, a few dozen complicated phases and a pretty rich phase diagram on its own is part of that reason. But just be aware, this is why we're saying the word ice, because originally this kind of physics, 2 in, 2 out, this correlation between you know, forcing these things to come up in pairs like that, this originated with the study of proton disorder in water ice. Okay, so does this actually exist? Well, I told you there's 2 key facts you need to know. One, that there's many, many ground states, and 2, that these ground states are composed of these loops of magnetic dipoles, right? So experimentally, you would like to know, you'd just like to establish both of these things before you say there are magnetic monopoles in these systems, right? So experimentally, we already know that this statement that there's many ground states would give you this finite residual entropy at low temperature. For closed loops, it's a little more subtle. You have to look for what are called pinch points in the spin-spin correlations. So let me just go through if these are seen in materials. So signature number 1 is this residual entropy. So if you remember from a thermodynamics course, the way you access your entropy is you measure something like heat capacity and then you integrate it. That will give you differences in your entropy. So if you want to know, for example, your entropy at low temperature, what you might do is you might say, well, at high temperature, I can figure out what it is. These are Ising spins. I have 2 states. I know I should get an R log 2 at high temperature, right? And then by integrating this heat capacity, which you can easily measure, or not easily, but you can measure, you can get this difference, right? Known value, value you don't know, thing you can measure, right? So that's exactly what you do. And what they find is if all the entropy was released, if there wasn't this macroscopic degeneracy, this large number of states, what they should end up with for this entropy is up here, R log 2. What they actually end up with is down here. Okay, something like 20, 30% lower. And so if you go ahead and you compute, you can't do it exactly, but you can do it reasonably well. You compute how many of these states there are, and thus what that residual entropy should be. What you find is that it's about 0.2 of R, and it matches this missing entropy almost perfectly. Okay. So this is the heat capacity. This is measured entropy data inferred from the heat capacity for this dysprosium titanate material. So this is clear evidence of a very, very large number of states present at low temperature. And those states have exactly, there's just the right amount of them to be these 2 in, 2 out states. The second signature is a little more subtle. So here you have to look at neutron scattering measurements. So it's a little complicated what they actually measure here, but it's essentially related to this spin-spin correlation function, which measures essentially how correlated 2 spins are in real space and then Fourier transforms it. Okay, so I won't be able to give you a full explanation of this, but I can make it somewhat plausible that these loops should give you some really long range correlations in real space. And then that should tell you something about what happens when you Fourier transform it. The way to see that is, well, these things are forming loops, right? So if I take one spin, I know it's in some loop, and this loop might be very, very big. It might go across the whole system even, right? And if I know that this thing is on a loop, then I actually, if I know what direction this spin is pointing here, I know something about the direction this spin is pointing here, right? For example, since this is on a loop, I know this spin can't be pointing in the opposite direction. And so that induces a correlation between 2 spins that are very far apart. And if you work out what that means when you Fourier transform it, what it leads to are these very sharp looking features in the Fourier transform of these spin-spin correlations, right? Something long range in real space gives you something sharp in Fourier space. And so these are called pinch points. And if you look at the experimental data, which is measuring essentially the same thing that's being computed on the right here in some theoretical model, you can see that looks quite a lot like a pinch point, right? So it looks like this material. This is actually holmium titanate, the other sort of best material here, has these pinch points in its spin correlation. Therefore, it has these loops. It also has that residual entropy as well. So we should establish at that point this thing has magnetic monopoles. That's what we should conclude. You might not be fully convinced by that. You might want, like, can we just like trap a magnetic monopole or do something a little more direct? People have tried, and they're in principle possible. No one's succeeded yet. These are mostly experimental issues. I don't think anyone doubts that these things really exist in the materials at this point, but no one's managed to give a more direct measurement. People are still trying. This, for example, is a recent paper where they are proposing to essentially take a very, very sensitive magnetometer, either made up of individual atoms or diamond nitrogen vacancies, or I think that's a small squid loop, and then try to measure fluctuations in the local magnetic field as these monopoles diffuse around. It's a bit subtle, but it's a little more direct than what we've described. So far, though, it hasn't been successful. Okay, so I've given you a very specific picture of how we went from frustration, which gave us all these ground states. Those ground states were correlated. In this case, it gave you these loops, and you can think of these loops as being a kind of constraint on these states, just like div.b = 0. And then when we broke these constraints, we had excitations with weird properties, in this case, magnetic monopoles. So this is part of a broader theme of, now I'm realizing I'm running out of time. So I'm sorry about that. Chitra, how long can I go over, do you think?
I think the plan is to finish at 5.
Okay, well, I'm gonna have to go very fast then. I apologize. So this is let me skip some of this. Let me keep with this though. So this is part of a more general picture of frustrated systems, where frustration gives you this extensive ground state degeneracy, and this can lead to states called spin liquids. These spin liquids, because of these constraints, are typically described by what are called emergent gauge theories. And these emergent gauge theories, their excitations are generally fractionalized. They have these properties that are sort of parts of the excitations of the original system. Since I've clearly not planned my time accurately, I'm going to skip that and go directly to this and tell you a little bit about some work that we did recently on spin ice thin films. Hopefully this will be sufficient justification for this pun about skating on spin ice, given this is a film of something with the word ice in it. So the idea of this work was to look at what happens to these spin ice systems when they weren't bulk crystals, but when we actually made atomically thin films, or really when someone else made atomically thin films and we thought about how they should behave, right? And so you can do this. They've been starting to do this in the past few years, and they can grow these things along several different crystallographic directions. And recently, they've actually been able to, in the last year or two, they've been actually able to get down to only a handful of layers, like, of order less than 10 atomic layers of these things. So this is a sort of a cross section of it where you have, here's 5 layers thick. There's a surface, 3 layers thick. Here's one, the smallest type of film that's still really pyrochlore, 1 layer thick, right? And here the growth direction is along the z-axis along 0, 0, 1. So the question is, what happens to spin ice when we confine it like that? So the answer depends on what we actually do at the surface. And so at the surface, because you've cut this thing, you actually end up modifying the exchange interactions. So while these tetrahedra are complete, they look just like they did in the bulk for most of them. At the edge, you have these bonds that are not part of any tetrahedron, right? We call these orphan bonds. And it's reasonable to expect that on these orphan bonds, the exchange interactions are going to be significantly modified, right? And there's 2 obvious possibilities, like I told you before. One is that they're antiferromagnetic like the bulk. The other is that they're actually ferromagnetic, different than the bulk. So it turns out these end up giving 2 distinct results. One is something analogous to 2-dimensional spin ice, like square ice. Another one is something entirely different, a new kind of spinlet. So let's do the familiar case first. If it's antiferromagnetic, everything almost works out the same as before. In the bulk here, away from these surfaces, these arrows still are joined head to tail. But as we get to the surface, because these things still want these things to anti-align, these things still go head to tail. So the loops have no trouble. They just close. They can run along the surface. There's no issue there. Okay, so here what you get is kind of boring in some sense. You get exactly the same physics you got in the 3D case, just restricted to 2D. And you see that same correlations, those same pinch points that you saw there, just restricted to 2 dimensions. Okay. The other case is a little more interesting. Here, if those extra bonds on the surface want the spins to align, then what ends up happening is that the loops can't actually go along the surface, right? If I'm going head to tail, head to tail, head to tail, if these want to go the opposite way, then I'm gonna have to go head to head at the surface, right? Which means the loops can actually terminate at the surface, but they can only terminate in pairs, right? These 2 spins have to be the same, which means if this loop stops here, there has to be some other loop that also stops there, okay? So because we break these loops, we break we no longer have these long range correlations. And so those pinch points we had are actually gone. So these correlations are no longer long range, they're actually short range now. And so when you do the Fourier transform, everything just looks fuzzy. Okay, so this is a new kind of spin liquid. And the pairing of these loops actually changes the structure of this thing. And so it's a bit of a subtle thing thinking about these loops, but there is an idea known as what's called topological degeneracy for spin liquids, which actually distinguishes between this antiferromagnetic and this ferromagnetic case. Basically, if you thought about loops in a plane, so for example, in a plane here, a square, if I thought about loops, every one of these loops is in some sense deformable into every other one, right? If I take this big loop here, I can squeeze it and shrink it and deform it into this little one or this big one or whatever. There's no obstruction there, right? More technically, in a plane, all loops can be collapsed to a point. But if you do something, for example, on something topologically non-trivial, like a torus, there are loops where that's not true, right? If I drag my loop around this hole of the torus, there's no way to collapse this to a point, right? It's stuck. Similarly, if I do it around the sort of donut hole there, a similar thing happens. So you have these 2 kinds of loops, spanning loops, that you can't deform into these smaller loops that you can collapse to a point. And this actually depends on the topology of manifold you put this thing up. So in this antiferromagnetic case, the number of these spanning loop is actually conserved in each direction. You can think of this as being sort of the magnetic flux through the holes of the torus. In the Z2 spin liquid, well, we broke the loops, so that can't be conserved anymore. But because we always paired them up, the parity of the number of loops is still conserved. So whether there's an even number of loops going around these holes or an odd number of loops, that still holds, right? And that defines the Z2 even odd spin liquid. So this kind of topological degeneracy, these loops that you essentially can't deform to points, this is sort of the same principles that one finds in quantum computing when one constructs error-correcting quantum codes. Okay, let me skip that since I'm out of time. Let me just summarize. Hopefully I've convinced you that frustration can lead to new and unusual physics. This includes emergent gauge theories, fractionalization, spin liquids, and also new kinds of quasi-particles like magnetic monopoles that you can't realize in a vacuum. And I hope you've noticed that this is related to all sorts of a large slate of ideas in high energy physics and quantum information, sort of touches on a lot of different fields. And there's lots to do here. So even pyrochlore spinices, which have been studied for at least 20 years now, still have surprises left to uncover. And to understand these things, you actually have to go through a pretty good cross-section of physics. So things like electromagnetism, atomic physics, some chemistry almost, solid state physics, all of these things get tied together when you think about quantum magnets and quantum materials more generally. And new materials are being synthesized at a pretty alarming rate. So there's always more to do. And if you want to know more about what I do, you can go to my website listed there, jeffrau.ca. Just a sort of advertisement for me and my hopefully future group is doing things like understanding how exchange works in rare earth magnets, whether we can get new kinds of frustration. Rare earth pyrochlores like spin ice that have stronger quantum effects. Everything I described to you at this point has been classical, but you can add quantum mechanics to it and get something like what's called quantum spin ice, which not only has an emergent magnetic field and emergent monopoles, has emergent photons and emergent quantum electrodynamics, right? And there's also more exotic versions of these kinds of spin liquids or these kinds of fractionalizations. For example, in cadaver materials, you have emergent Majorana fermions, right? And this is these kind of connections to high energy physics. These are tunable with things like electric and magnetic fields. And if you're interested in these kind of things, or you know someone who's interested in these kind of things, I am looking for people at all levels. So please get in touch. And I'm sorry for going a little bit over, and hopefully I didn't talk too quickly at the end there. I did want to get somewhat on time. So I think I am done.
Great, thank you, Dr. Rau. We do have a little bit of time for questions. People can either raise their hand. So if you go to participants and next to your name, you can either raise your hand, or you can put your message in the chat and you can ask your question in the chat, or there's an email address that's been given. So I'm just going to stop the recording and also just remind everybody that we will continue with our next seminar next Friday at 4 p.m. and open up the floor for questions.